up and go over these concepts. Here's the deal. I understand sometimes we forget things that we haven't used a whole lot, but I do want to point out that numbers 1 and 2, which I'm seeing blank on a lot of papers, we talked about this school year in geometry. I see Hannah.
And if those students are present in your class, please send them to the seminar room at this time.
Hey Cheryl, I don't know how to get a hold of Jerry in the seminar room, but I sent Hannah Pittman about probably 10 minutes ago to go to the seminar room, so she should already be there. Is that what I need to call? 150? Okay, thanks. Hey Lisa, is Hannah Pittman not in the seminar room? I sent her about 10 minutes ago to the seminar. Okay, they called her name over the intercom, so I was just making sure. Okay, perfect. Thanks, bye-bye. Okay. I know. Oh, well. Okay, guys. I was trying to cover it. Yes, sir. 12-2. Anybody else not have a 12-1 and a 12-2? Okay. So, first of all, the concepts that are on the warm-up are very important. That's why I put them on the warm-up. They are things you're going to have to be able to do for this chapter. All of the things on the warm-ups are Algebra 1 skills, but some of them we actually did and reviewed and talked about this school year in geometry. And all of the 4 things on this first 12-1 we did this school year. Back when we talked about writing equations of lines, we did numbers 1 and 2. What kind of line is number 1? FG. Talk to me, guys. What kind of line is number 1 FG? Vertical. Vertical lines have a special rule. They are not written in the form y equals mx plus b, which is your equation of a line in slope-intercept form. They are not written in point-slope form. Vertical lines have a special equation for them. What is the equation for any, not just this one, any vertical line? Nobody knows? Okay, this is not good. You need to write down notes on your paper. Again, not only is this important for geometry, this is important for Algebra 2. So you have to be able to write equations of vertical lines. So on your paper, take notes. Vertical lines. Vertical lines are always written as x equals a number. X equals a number. Didn't say it, Kristen. Say I did it. I think this was it. All right, so x equals a number. What is the number that x is equal to for line FG? -2. X is -2 everywhere on that line. Y is constantly changing. We have a point at -2, 0, -2, 1, -2, 2. But x is always -2. So when it's vertical, it should be x equals, and then the answer is whatever number that is. X equals, in this case, -2. So the equation for number 1 should have been x equals -2. Number 2, what kind of line is number 2? Horizontal. It also has a special rule. Horizontal lines are not written in the form y equals mx plus b either. Horizontal lines are written how? Y equals. Good. We're starting to get the hang of that. So horizontal will be y equals a number. And so then you ask yourself, what is the y value that is constant for that line EH? 3. Does everybody agree that we have a point at 1, 3, 2, 3, 3, 3, 4, 3, but the number that doesn't change is the y value? So it is y equals 3. Is that coming back to you now? All right, so we talked about that back, I can't remember what chapter that, I think it was chapter 3, sections 5 and 6, writing equations of lines. And then again, you should have learned it in Algebra 1 as well. But what's important is that you know it now, leading into this chapter and then going into Algebra 2. Any questions on how to write the equation of a vertical or a horizontal line? Corbin, are we good? All right. Number 3. So on number 3, what do we need to do first? Distribute. And I saw most of you were working on 3 and 4. 3 and 4 were just our basic algebra problems. We've been using algebra all year long in geometry. So what is 2 times 25? 50. And then 2 times negative x? Good. Equals x plus 2. And then from there, we could add 2x. We want to do the opposite of subtraction, which is addition. I also heard someone say subtract, and what were you going to subtract? 2. So you could have moved the 2 to this side first and then added the 2x or vice versa. The order doesn't matter there. So if I add 2x first, I'm going to end up with 50 equals 3x plus 2. And then I'm going to go ahead and do what you said, subtract 2 to the other side. So that we have 48 equals 3x. It's in the library. It's not really toys. It's just in the library. They do. Okay, so what do we do next? Divide by 3. And what do we get for x? X equals 16. Questions on number 3? Okay, number 4. Let's go with Michael. What would I do first? Very good. Subtract 3x. And so as long as we do that, we should end up with 8 equals x. So that was super quick and simple, right? Any questions on 3 or 4? All right. And I figured that part was easier. This part, every year, people forget how to write equations of lines, but I want you to try and not just throw your hands up. So if you don't understand anything on 12.1 now, ask. Anybody have a question on anything with 12.1 at this point? Okay, we're going to go ahead and switch over to 12.2 and look at the warm-up on it first. And again, this is important for where we're headed in these sections today. So what percent of 60 is 18? Let's just start with some answers. Anybody get an answer? Don't be afraid. It could be wrong and it's okay. 3.3%. Somebody get a different answer? 7.8%. Different answer? 30%. A different answer? 10.8%. Anybody get a different answer? 33.3%. Okay, so we have a lot of different ideas. Let's talk about different ways we can work the problem. So I'm going to show you the teacher algebra way that you could work the problem, and then every year I have students who show me different ways that they worked it, and as long as your way gets the correct answer, I do not care how you set it up. You don't have to do it my way, but this is just a way that would work, okay? So first of all, it says what percent. When we don't know something in algebra, what do we put in its place? X. So what percent, so we're looking for X percent of, what does of typically mean in math? Multiply. So X percent times 60 is, what does is usually mean? Equals 18. So it says X times 60 equals 18. So what would we do from there to solve for X if X is being multiplied by 60? Divide by 60. So we would take and divide both sides by 60. And so we end up with X equals, what is 18 divided by 60? What is it? 0.3. But that is the decimal value. We want to know the percentage. So how do you take a decimal and change it to a percent? Okay, we multiply by 100, which moves the decimal 2 places to the right. So if we move that decimal 2 places to the right, what do we have to put as a placeholder? a 0. And so this becomes 30%. Okay, so whoever got 30, that was correct. Those of you who did not get 30, that's okay. Thank you for giving your answers. Questions, though, on how I set that up or how you would work it? Did anybody do it a different way than what I did and still get 30? Ruben, what did you do? Here. Okay, so what did you actually write on your paper? Do you?
I just thought of it like a 10.
Mm-hmm. Okay, so you basically did the same thing. You just said 18 divided by 60 times 100. Landon, or not Landon, Trey, did you do something different? Okay. Okay. All right, so any questions at this point for number 1? Okay, number 2. Answers that you think you have for number 2, and then we'll check and see if you're right or wrong. And don't be afraid, please, to say your answers. Yes, sir. 2.64. Somebody different answer? Andy, do you have a different answer? Okay. All right, so let's go through. I'm going to again show you my way that I would do it, but you can, if you did it a different way, please let me know. What number? So when we don't know something in algebra, we put X. Is means equals 44%. How do you write 44%? 0.44, 0.44. You move that decimal back 2 places to the left to put it back in decimal form or divide it by 100. So 0.44 of means what? Multiply times and then 6. So when you see that word is, think equals. When you see that word of, think multiply. And if you don't know what something is, put a variable in its place. So we have x equals 0.44 times 6. If you take your calculator and do 0.44 times 6, do you get 2.64? Awesome. Questions on number 2? Okay. Anybody do it differently? Yes, sir. Okay, so you did 6 divided by 100, which gave you 0.06, and then multiplied that by 44. Okay, awesome. Anybody do it different? Okay. All right, number 3, I want you to find the measure of angle WVX. First of all, I want to point out some chapter 1 notation. We're in chapter 12. It's been a long time since August where we wrote correct notation for naming angles and measures of angles. So just a reminder, if you're giving me the measure of an angle in this chapter, you have to put the little m. If you're just naming the angle, you take off the little m. And we worked on that a bunch all through first semester. So they want the measure of angle WVX. WVX, we go from W to V to X. We're looking for that angle. That angle is what percent of the circle? 29% of the circle. How many degrees are in a circle? 360. So if we want to know what is 29% of the circle, and we know the circle's 360, what would we do on our calculator or by hand? Very good. We would take 29% of 360, which means we would take that 29% and write it as 0.29. Of means multiply 360. And what is 0.29 times 360? 104.4? Okay. So 104.4, and what do we measure angles in? Degrees. So don't forget your degree symbol. Questions on number 3? Okay, so what's most important, not that when you walked in you were able to answer all 7 questions, but what's important is that you understand how to now. Any questions on those 7 warm-up items? Okay, I need to warn you, we are down to 18 school days and we have to cover all of chapter 12. We have to review it and test it. We also need to have some time to review for the final. And so that's going to push us to doing 2 sections every day so that we have time to work on reviewing for the final. That is not anything abnormal. We've always done 2 sections a day, except in chapter 11, I slowed us down to 1 section a day, mainly because I threw in surface area, which our book did not do, and we needed allocated some time to work on that. So we are used to doing 2 sections a day. We just haven't done it in a little while. So we're going to have a lot of notes today. Chapter 12 is heavy on, I don't want to really say rules, but theorems that you have to understand. You don't have to memorize the name of the theorem. You don't have to be able to write the theorem. There are no proofs. But you have to know what the theorem says in order to solve a problem. So it's going to be heavy on theorems, which you can think of as rules if you want to, that you're going to have to memorize in order to work problems. That's the hardest part of chapter 12. It is not a hard chapter, but if you don't know your rules, then you won't be able to work the problems. So it's kind of like formulas in a sense on the chapter 11 test. If you didn't know your formulas, you couldn't work the problem. If you don't know the rules, you can't work the problem. But if you know the rules, the math is going to be really easy. Okay? There's a lot of vocab in chapter 12, and so we will have a vocab test again. We will not have a formula test this time. It'll just be a vocab test. There's not really formulas in chapter 12, but there again are a lot of rules, a lot of theorems that you have to know. All right, so we're going to go back to 12:1 if you'll switch back to your notes. And by the way, we will look at the chapter 11 test, but I have a student taking it right now today, so I didn't want to start the class period with that. If we have time at the end, we'll look at it today. If not, we'll do it next class period. Okay, so big idea for today is we're going to learn a lot of vocabulary in section 1. It's just tons of vocabulary. We're going to talk about what's a tangent, what's a secant, what's a chord. You're going to have to pick out those things in the picture and name them with correct notation. This first section is going to be heavy on chapter 1 notation again. Can you name a segment? Can you name a line? Can you name an array? Those kinds of things. And as you can see, it is full of vocabulary in section 1. And then in section 2, we're going to focus on what are called arcs and chords. And so if you look, you can see that's what our plan was for today. There are 7 sections in chapter 12, by the way, so we'll do 1 and 2 today. Next week, then we'll group 3 and 4 together, 5 and 6 together, and then section 7, sounds like we're going to only do section 7, but really we're going to add in some things in section 7, so it's going to be a little deeper than just what's in your book in 7, okay? And then we'll review, test, and then we'll start reviewing for the final. By the way, I do have the review for the final that I plan to go ahead and hand out today before you leave, just to get it in your hands. If you don't have to take the final, I'm still going to collect the review for a grade because my plan is to spend at least 3 days in class working on it. And so I want you to review for that as well, and just it's not going to hurt you to go back and review your geometry. So it will be for a grade even if you're not taking the final. Okay. All right, I'm going to skip this. It's just kind of like FYI. The only thing I want to point out on this little side right here is just a reminder of how you name a circle. We've already talked about that. We did that in the last chapter when you had to name the base of a cone or a cylinder. So just make sure that you are naming a circle correctly. In chapter 12, it's just all about circles. You cannot tell me what was on the ACT Aspire test. Legally, I'm not allowed to talk about that test with you, so please don't talk about it with me. Don't tell me that you had a dream about circles last night and tell me what you dreamed about. I've had students do that before. Miss Lush, I had a dream about this problem. Can you show me how to work it? Right after the ACT Aspire test. You can't do that. But if there were questions about circles on there, we hadn't got to that. So don't stress about it, but that's what this whole chapter is all about. First 2 vocab words should be kind of common sense. When you think of the interior of a circle, where should the interior be? Inside. And if you think exterior, where should it be? Outside, and that's all it is. Interior of a circle is the points inside, exterior is the points outside. So some of these vocab words are not difficult. Then these 3 or 4 vocabulary words are super important for chapter 12. You are going to be asked to identify what is a chord, what is a secant, what is a tangent, and what is the point of tangency. All right, so let's start with chord. A chord, first of all, is a segment, not a line. It's just a segment, and its endpoints lie on the circle. So when you look at the picture there, do you see how AB is a segment and its endpoints touch the circle? That is a chord. Here's the tricky part. When you look at the blue line, which they've labeled secant, a secant contains a chord. Do you agree that there is a segment on the secant that still touches both parts of the circle? You guys with me? So it's going to depend on how you name that as to whether or not it's a secant or a chord. A secant is a line, not a segment. And it intersects a circle at 2 points. Very important that it's at 2 points. So here's the thing. If I write CD with a segment above it, or I write CD with a line above it, those mean two different things in this picture. What is this first one going to be? A chord. A chord. CD is a segment with the line above it, just the segment above it. What is this going to mean? Secant. Secant CD because it's going through the circle forever. So a secant contains a chord is a segment, a secant is a line. They're basically the same thing. They touch a circle at 2 places, but one goes on forever and one stops. Any questions about a chord and a secant? Okay. Tangent. A tangent, the only difference between a tangent and a secant is that a tangent is also a line, but it intersects at exactly 1 point. So notice the green line. It only touches at 1 point. It only has 1 point on it. Vasai, you with me? I'm tired today. If you need to, feel free to stand up in the back, okay? All right, so if I look at that line, we need to go back to chapter 1 and remember how to name lines. One way to name a line is by using 2 capital letters and putting a line above it. Another way to name a line was to put the word line and then remember to use that little cursive letter that's out to the side. That is not a point on your line, it's just a way to name it. So I could call that line M. Everybody remember that from chapter 1? So line M is a tangent line because it only touches at 1 point. And the point where it touches is called the point of tangency. It's the place where the tangent line touches the circle. So a point of tangency is just a point where the tangent and the circle intersect. Okay, you need to know the difference between chord, secant, tangent, and point of tangency. So let's look at an example. On your homework, I need to warn you that they may not write these words, which makes it a little bit harder. They may just say, here's a picture, identify each line or segment that intersects circle L, and that's it. So you are going to need to look back at your notes to make sure that you're listing every one of these. Are you guys with me? Okay, so again, on the homework, you'll have to write down chords, secant, tangent, diameter, radii, and then list all of those things in your picture. So it just said line or segment. We're not talking about points of tangency on this example. So let's start with a chord. Does anybody see a chord in the picture? KM. So KM. I don't think we have a line that goes from K. Yes, we do. What am I talking about? KM. Thank you very much. And when I name it, do I put a segment or a line with arrows? Segment. Okay. What kind of chord is KM? It's special. It's what? It's the diameter. The diameter is a chord. So when we look down here at diameter, we're going to put KM. So it's going to go in 2 places. It's a chord, but it's also the diameter because it goes through the circle. All right? Are there any other chords in the picture? JM. JM, again, when you look at JM, do you put a segment above it or a line with arrows? Segment, because you're talking about it as a chord. Are there any other chords in the picture? Nope. All right, secants. Do you see any secants in the picture? JM again, but this time when you write the secant JM, what do you have to put above it? Lines with arrows. The only difference between a secant and a chord is a secant goes on forever and a chord stops at the end of the circle. Okay? Are there any other secants in the picture? No. All right, tangents. Do you see any tangent lines? Line M, and again, make sure you put the word line and then use the little lowercase letter that's out to the side. You cannot name a line with 1 letter. You have to have 2 letters if you're talking about 2 points on your line. Otherwise, you use the word line and the little lowercase cursive letter. All right, we've got the diameter, KM, so the only thing we're missing now is the radii. Are there any radii in the picture? JL, I heard. Make sure you put it as a segment. What else? LK. What else? LM or ML. Either way. So KL and ML. Remember, when you name a line segment, the order doesn't matter. Same with a line. So just pick the two letters in either order. Any questions on chord, radius, diameter, secant, tangent? All right. Easy enough. Okay. So some more vocabulary. Congruent circles, concentric circles, and tangent circles. Obviously, they are all what? Circles, but you're going to have to understand the difference between the congruent, concentric, and tangent. So starting with congruent, what do you think congruent means? The same, equal. So for two circles to be congruent, here's what has to be true about them. They have to have congruent radii. For them to be congruent, they need to be the same size, and to be the same size, they need to have the same radius. So same length of radius. So as long as AC is congruent to BD, then the radii would be congruent, so then the circles would be the same size. Does that make sense? Okay, and then just some notation. Here's a way you can say two circles are congruent. Name them as circles, put the little congruent symbol between them. All right, concentric. When I think of concentric circles, I think of like a dartboard. Concentric circles have to have the same center, and then they just get bigger or smaller from that center. So if we look here, the blue circle and the red circle have the same center. So we would say that they are concentric. They would be named the same name. So if I put a letter here like A, they would both be called circle A. The only way to be able to identify which one we're talking about is we would have to have more information in our picture. Does that make sense? Okay. And then tangent circles are going to be two circles that do what? Touch and intersect at one point only. For them to be tangent, they can only intersect at exactly one point. So you have two different ways they can be tangent. They can be internally tangent, where they are inside of each other, or they can be externally tangent, where they are not inside, they're outside, but they're touching at one point. Do you see the difference between internal versus external? Any questions? Okay. Moving on quickly. So let's see if we can answer all of these questions, and these are going to go back to the bell work, to the warm-up. So first of all, find the length of each radius. When you answer these questions on your homework, make sure you identify which circle you're talking about. How many circles are in the picture? 2. So on your paper, you would do something like circle S, and then you would list the radius. What's the length of the radius for circle S? Okay, so if you look at where this point is, it is about halfway up to here and then on up another hole. Or you could go out this direction, or you could go this direction or this direction. Up and down, you can see a little easier that the radius is about 1.5 or 1.5. Then identify the other circle, circle R. And what is the radius for circle R? 2. So you would say the radius is equal to 2. Okay? Yes, sir. If they don't give you units, I'm not going to be picky about that. If they gave you units, I would expect you to put them, like inches, miles, feet. Otherwise, you don't have to put the word units unless you want to. But it would be measured in units of some sort. Okay, second part it says is identify the point of tangency. So again, on your paper, you would need to put something like P of tangency or point of tangency. Identify what you're writing down on your paper. So my point of tangency. Where is the point of tangency? Very good. When you look at the picture, your point needs to be a coordinate since you're on a graph. They touch right here, and that's at -2, 0. So your point of tangency would be an ordered pair, -2, 0. Okay, next thing it asks you for is the equation of the tangent line at this point. Okay, a tangent line is where the two circles touch at that point. So how would I draw a tangent line at that point? What kind of line would I draw? Vertical, so it would go this way. Okay, remember that tangent lines only touch the circles at one point. So vertical wouldn't work. What would it need to be? Horizontal. So this is the tangent line. This is the point of tangency. They want us to write the equation, just like the bell work, of that tangent line. So what is the equation of that tangent line? Y equals, because it's horizontal, so the tangent line would be y equals, and then the value of y at that line is just 0. Questions on this example? Please ask if you're lost anywhere. And where are you headed back to? Right, that's right. Thank you. And then just don't forget about the bonus if you want to do that. Turn it in tomorrow, okay? There you go, man. See you later. Okay, moving on. Couple more vocabulary words. So common tangent, and then we're going to talk about them being internally versus externally tangent. So a common tangent line is when two circles both touch a line, the same line, at only one point. So would you agree that this line at the top is touching both circles and only at one point each? And the same at the bottom, right? So they have a common tangent, a tangent line that touches two circles at only one point. When you look at those common tangents can be commonly internally tangent or commonly externally tangent. There is a type, never mind, this is right. So these two lines would be considered common external tangents. Look at the difference, and then maybe it'll make sense why the next ones are called common internal. Do you agree that the two blue lines also touch each circle at only one point? So they are a common tangent, but these are called common internal tangents. So what's the difference between a common internal and a common external? How could you describe the difference between the two blue lines being commonly internal and the two red lines being commonly external? Michael? Very good. The internally tangents are going in between the two circles. The way the book's going to describe it is they're going to say if you were to connect the two centers with a line segment, if that line segment does not cross the tangent lines, then they are externally tangent. If you look at the other picture, you connect the two centers, they do cross the tangent lines, so they're commonly internal. Does that make sense? So a common tangent is a tangent line they both share, and then commonly internal means that they're going to go in between the two circles. All right. Here is our very first rule, theorem, that you're going to have to know for your test. Again, you do not need to know the name of it. You don't need to be able to write it. You need to be able to use it in a picture. It goes both directions. It looks like it's two theorems, but it's really the same theorem. It's just both directions. Biconditional is what we talked about that being. So if a line is tangent to a circle, look at the red line. Would you agree the red line is touching that circle at one point? Okay? If a line is tangent to a circle, then it will be perpendicular to the radius drawn to the point of tangency. In other words, if you were to connect from the center up to the point of tangency where it touches, that radius and that tangent line are going to form what? A right angle. They're going to be perpendicular, so they're going to form a right angle. Okay, so if I were you, I'd draw a right angle box there on my picture. Here's where that's going to come into play on the homework. If I connect this point A over to a point on the line, what do I end up creating in my picture? A right triangle. And so you're going to see some right triangles pop up on the homework in this lesson, okay, in this chapter. It goes the other direction as well. If they don't tell you that this is a tangent line, they don't tell you this is a point of tangency, but the radius makes a right angle with the line, then this line must be a tangent line. So when you look at the picture, they might tell you L is tangent, therefore you know it makes a right angle, or they may tell you that it's making a right angle, so you can now say it is a tangent line. A tangent and a radius make a right angle. That's the key. Any questions? Okay, the only thing I want to emphasize one more time is it has to be at the point of tangency. It doesn't just make a right angle with any point on the line. It has to be where the line touches the circle. Is that clear? Okay. Second theorem or rule that you're going to need to know for the test is this theorem here. Again, it doesn't matter the name, it doesn't matter what all it says, you just need to understand the idea. So it says if you have two segments that are both tangent to a circle from the same exterior point, when you look at this picture, do you agree that AB and AC are both tangent? They're touching the circle at one point? And would you agree that they both start at the same point outside the circle, point A? Then all you need to know from this theorem is that means that AB would be the same length as AC. Woo. So AB and AC are congruent. So if you have two tangent lines coming from the same exterior point, then those segments will be congruent. Okay, a lot of vocab, two rules in section 12.1. Questions so far? All right, so look at this last example. What does it tell me about HK and HG? They're tangent. What point do they start from? H. So what should that mean about HK and HG? That they're equal. And then the algebra becomes really simple. What would I write down on my paper to find the length of HG? 4 plus 2a equals 5a minus 32. I promise you that the math won't be hard. It's the theorems and knowing what you can do that is the hardest part of chapter 12. From here, we practiced in the warm-up. It's really easy. What do we do to solve? Add 32. So we get 36 plus 2a equals 5a. What do you want to do from there? Subtract the 2a. So now we have 3a equals 36. From there, divide by 3. And what do we get for a? 12. Is that our answer? No. What did it ask you to find? HG. Now here is the one thing that I counted off for months back at the beginning of the school year. Over and over and over again, I kept writing it on your papers, circling it on your papers, writing notes on your papers. When you write your answer, HG equals. Thank you. You do not put a line segment above HG. You are just telling me the distance from H to G is equal to this value. So don't put a line segment, okay? So HG should have been 4 plus 2 times A, which we got 12. What's 2 times 12? 24. Plus 4 is 28. So your answer would be HG with no line segment equals 28. All right, would you agree it's not hard? Would you agree there was a lot of information packed in 12.1 notes? So what you need to do when you're working on that homework is go back and study your vocab and study those two rules. There's only two in 12.1. And one more time, I'm going to write those two rules on the board before we jump to 12.2. If you have a circle and you have a tangent line to that circle, the radius will make a right angle with your tangent line. Okay? Second rule we just learned was if you have a circle and you have two tangents that come from the same exterior point, those two tangents will be congruent. Questions? Okay, and the rest of it was just vocab and understanding the vocab. So move on to 12.2. And this is where we talk about arcs and chords. We already looked at the warm-up. And again, you're going to notice more vocab, lots of vocab in chapter 12. In fact, I think there's 20, I may be lying to you here, but 26 words, something like that. So it's a hefty vocab that we're going to end the school year with. Not as much as the first chapter. Do you guys remember how many words there were? 50. So 26 is a lot, though. So you're going to have to make a good Quizlet and study, okay? Make some vocab flashcards, whatever, but there's a lot of vocab. It should be a good 26-point test grade. You should all make 100. It should help your grade. But if you don't study, it's not going to help your grade. So make sure you start making a Quizlet right now or flashcards right now. Central angle is our first vocab word. This is huge for this chapter. You're going to need to know what is a central angle versus other angles we're going to learn next week. We're going to talk about inscribed angles, angles that are inside the circle, angles that are outside the circle. Central angles are angles whose vertex is the center. Central, center. Okay? The vertex is the center of the circle. So if you think about drawing a circle, goes back to the Bellwork question. If this is the center of my circle, then this would be a central angle because its vertex is at the center. Okay? An arc. An arc is a piece of your circle. It is an unbroken part of the circle. Unbroken just means you don't want to split it into pieces. So it's just continuous from one endpoint to the other endpoint. What I marked in red there would be an arc. It is just a piece of the outer circle. Okay? Any questions there? All right. Here's the thing that I don't think they put in the notes yet. It's coming up maybe in a minute. I want you to go ahead and add to your notes. The measure of an arc is equal to the measure of the central angle. And I just put little M for measure. If you need to write out the word measure so you'll understand your notes, do that. Measure of the arc is exactly the same as the measure of the central angle. So if I tell you that this angle is 30 degrees, then this arc, AB, is also 30 degrees. Okay, now we're going to talk about how do I name an arc, how do I write it, what kind of arcs are there. Any questions, though, on this part right here? Okay, so the next thing is the different types of arcs. There's a minor arc, a major arc, and then a semicircle. And on the homework, they're going to ask you to identify what kind of arc is it. So let's start with semicircle. I'm going to go bottom up. When you think of the semicircle, what do you think of? Half of a circle. So a semicircle is going to be half of a circle. So what's the measure of every semicircle going to be? 180. When you name a semicircle, you can either name it with 2 letters or 3 letters. It doesn't matter. 3 letters is what they did here. So E, F, G. The middle letter helps identify which direction you're going. So I'm going from E to F to G. Otherwise, if I just put measure of EG, sorry, this isn't not writing correctly. I'm going to go to the board. Ignore that down there. That's bad. So I'm going over here to the whiteboard. If I just write measure, just kidding, it's the end of the year. All right. Measure of EG. And put an arc, it's got an arc above it, not a line segment, not a line, not a ray, it's a curved arc. If I just put EG, you're not going to know if you're supposed to go up E to G or down E to G. Does that make sense? So that middle letter is nice because it tells you the direction. But would it matter if I was asking for the measure of arc EG, which direction I went? No, it wouldn't matter. It would still be 180 degrees. So that's why you can name it with 2 letters or 3 letters, because it wouldn't make a difference unless you're trying to identify the actual arc you're talking about. No, good question. EGF, completely different arc. So I'm going to trace it, okay? EGF would be starting at E, going to G, and then to F. So it would be all of that part of the circle. So the first letter tells you where to start. The last letter tells you where to end, and the middle letter tells you the direction to travel. Does that make sense? Okay, very important. So semicircle is going to be half a circle. It's always going to be 180 degrees. Minor versus major. What do you think a minor arc is then? Smaller than a semicircle, so less than 180. What's a major arc going to be? Greater than 180. So a minor arc is an arc whose points are on or in the interior of the central angle. In other words, when you look at the picture, if this is your central angle, the minor arc is the arc that's in between that central angle. So from A to C would be the minor arc. Again, if they just want you to name it, you would put AC and put an arc above it. If they want the measure of it, you'll do like we did back in chapter 1. You'll put a little M and then AC and an arc above it. So this is how you name an arc. This is how you tell me the measure of an arc. Are you guys with me on the difference? Just like angles. The measure of the arc is exactly the same as the measure of the central angle. So here it is again in your notes. I had you write it down. It's right here again. Okay? So if I tell you that ABC is X degrees, what's the measure of AC? X degrees. Okay, they're the same. The measure of the arc and the measure of the central angle are the same. Okay, this is a minor arc. So again, direction matters. If I just put AC and only put 2 letters, here's the rule. If there are only 2 letters, that means it is a minor arc. You're going to go the shortest direction from A to C. 2 letters means minor. If it's a major arc, you have to use 3 letters to name it. And the reason you need that 3rd letter is to show the direction. Now I'm going to go from A to C, but I want to go a different direction, so I'm going to add another letter. ADC would mean to go all the way around through D. Does that make sense? Okay. Questions on minor versus major versus semicircle? All right, we're going to see. You guys are super quiet. I already said this. Here it is in your notes. Minor arcs are named by 2 points. Major arcs must be named by 3 points. Semicircles can be named either way because it won't matter. They're still going to be the same measure no matter what. So here we go. I'm going to call on you, so be ready. The circle graph shows the types of grass planted in the yards of one neighborhood. Find the measure of, what is it that they're naming there? Is that an arc or an angle? Arc. KLF. Now here's the thing I want to warn you about. Sometimes the book will name it with 3 letters and it turns out to be a minor arc. And the only reason that they do that is so you know the direction to travel. So just because they put 3 letters doesn't mean your answer is going to be greater than 180. It could technically turn out to be a minor arc, and they were just telling you what direction to travel. If you are naming it, though, and it's minor, you use 2 letters. If you're naming it and it's major, you use 3 letters. Okay? So KLF means we're going to start at K and go what direction? To the left through L. So K to L and then all the way around to F. So is that going to be a major arc based on the picture? Yes. It's definitely bigger than half the circle. Would you agree? Okay. So we want to find the measure of that arc. How much of the circle do we have there? 65%. Back to the bell work. What do we do to figure out the measure of that arc? If it's 65% of the circle, exactly how many degrees are in a circle? 360, and we want 65% of those degrees. So we want to take 65% of 360, which is 0.65 times 360, and what do we get? 234. Now remember, the measure of an arc is the same as the measure of an angle, measure of the central angle. How do we measure angles? In what units? Degrees. So how do we measure arcs? Degrees. So you would say the measure of arc KLF with correct notation equals 234 degrees. treat it just like you would an angle back in chapter 1. Put a little m, but now you're putting an arc above it instead of an angle symbol. And it's still measured in degrees. Any questions? Okay. So I'll let you guys try these 2 problems. Be careful and note, or 3 problems. Notice the difference. 2 of them are asking you to find measures of angles, and 1 of them is asking you to find the measure of an arc. But what did we say is true about the measure of a central angle and its arc? They're equal. Okay, go. You and your partner find the answers to those 3 questions. It's really hard to read on your paper, so you may need to look up here at the board to see the colors and the differentiation. I'll give you just a few minutes. Oh, sorry. Do you need me to give you any information, Corbin? Okay, let me know if you do. I think as long as you can see where the colors change, it doesn't really matter what color they are, you can answer the question. I'm going to come back, check it together, okay? So again, graph on your paper is not so awesome, but hopefully with it blown up, that helped a little bit. I'm going to go back. So again, writing notation, go back to chapter 1. Make sure you're naming your angle correctly using a little m if you're giving me its measurement. FMC means we're going to go from point F to point M to point C. So F to M to C, and we're creating this angle. So that means we need to add what 3 categories together to get that angle? Pop, country, and R&B. We're going to add all those together. We want that whole angle. So we're going to do 9 plus 10 plus 11. And what percent of the circle do we have then? 30%. How do we find the angle measure if we want 30% of the circle? 0.3 times 360. 360 degrees in a circle. What is 30% of 360? 108 degrees. Questions on the first one? Okay, part B. Now we're looking at the arc. Again, this is 3 letters so that it tells you the direction to travel. So we're going to go from A in the direction of H. So starting at A, you're going to go in the direction of H, meaning you're going to go to the left. From A through H and go all the way around to B. You don't cut across your circle. You're looking at the arc, which is the outer part of the circle. Okay? So from A to H around to B. How much of the circle is that? 75%. And you could have went and added all of these together, but what would have been the easier way? Okay, it's everything except what category? Rock, which is 25%. So 100 minus 25% would leave us with 75%. So this should equal 75% of the circle, which is 360. So what is 0.75 times 360? 270 degrees. Does that make sense though? Any questions? Okay, next one, angle EMD. Again, the first letter tells you where to start, the middle letter tells you the direction to go, but you're looking at the angle. Be very careful. So you're going from E right here to M up to D down. So EMD is just this one section. What section is it? Country. 10%. So what is 0.1 times 360? 36 what? Degrees. Measures of angles and measures of arcs are both measured in degrees. The angle will be the same as the arc if the angle is the central angle, and that means it has to have its center at the vertex, or the vertex is at the center of the circle. Okay. Any questions on that kind of concept? Again, how many letters do you use to name a minor arc? 2. How many letters to name a major arc? 3. And a semicircle is how much of a circle? Half, which is 180. Okay, so now we're going to look at adjacent arcs. What do you think adjacent arcs are? Arcs that touch. They have to share one common point. They touch at one endpoint. They do not overlap. They're adjacent. So if you look at the picture, RS and ST touch at what point? What point do they have in common? What point do they touch at? S. They are adjacent. They are arcs of the same circle that intersect at exactly one point. So adjacent arcs are just two arcs that touch at one point. Okay, and notice how they named them with little arcs above them. Okay, so now we're going to talk about the arc addition postulate, which we kind of already used. This goes back to segment addition postulate, angle addition postulate. Arc addition postulate just says that if you want to find the measure from arc AC, then you can just take arc AB and add arc BC to it. So the measure of arc ABC would be the measure of arc AB plus the measure of arc BC. Just add the two adjacent arcs together. That's all it means. So if this is 30 degrees and this is 20 degrees, what's the measure of arc ABC? 50 degrees. That's all there is to it. Okay? Again, not super important to me that you can say arc addition postulate. What's important to me is that you can find the measure of the arc. Is that okay? So just add the parts together. And that is the same thing we've been doing all year long. So here's where we start to get some more complicated problems, but this isn't super hard. What are we looking for here? Measure of arc BD. Now, it was only 2 letters. So what direction do we travel if there's only 2 letters? The shortest way. 2 letters means it should be minor. You're going the shortest direction. So is it the shortest direction to go to the right or to the left? To the right. So we're going to go from B to D to the right, and this is what we're looking for. What's the measure of that arc? So we're going to need to figure that out. Here are some things to remind you. What kind of angle is angle AFE according to today's vocabulary? What would we call that angle? If its vertex is at the center, it's called a central angle, okay? So what do we know? We learned this a long time ago. What kind of angles are these angles? Vertical. And what do we know about vertical angles? They're the same. So if this angle is 97.4 degrees, what other angle has to be 97.4 degrees? BFC, good. Now, I don't know if we needed that for this problem, but I just want to point that out because you may need that for your homework problems. So vertical angles are still congruent, and therefore if this angle is 97.4, this angle is 97.4. They're both central angles, so what does that make the measure of the arc from B to C? 97.4. Okay, now I want to warn you about something that's coming up next week. If I have an angle, and the angles are, a circle, and the angles are not at the center, the measure of this arc right here, AB, is not the same as the measure of angle AEB. Are you guys with me right now? This angle is not a central angle. Therefore, this angle does not equal the measure of this arc. However, are these two angles still vertical? So they're still congruent angles. But obviously, this arc is not the same as this arc, right? So just because the angles are congruent doesn't mean the arcs are unless they're at the center. If they're at the center, then they're equal. Okay, so great. This is 97.4 from B to C, but how do I find the distance from B to D? I'm going to tell you I really didn't even need to use this 97.4 here. So I'm going to erase it for now. I just wanted to show you that that was true. How can we find the distance from B to D, this arc measure? So what I think I'm hearing Peyton say is, what do you notice about this whole arc BCE? It's a semicircle. So because it's going This is the diameter of the circle. That makes this the semicircle. How much is a semicircle? 180. If this is 52, what could we do to find what's left from B to D? Just subtract. So 180 minus 52 is how much? 128. So the measure from arc B to D would be 128 degrees. Questions there? Look for your diameters. Those are going to help you determine where are your semicircles, and then that'll help you at least know the measure from those points. Okay. They did it a different way, which was much harder and not necessary. Okay, so look at this one. And I don't know why all this is written, so I'm going to scratch through it because I don't want you to have it, and it's not on your notes, right? Okay. So find the measure of arc LJN. Where do we start? L. What direction do we go? To the left, towards J. Be very careful. So LJN means start at L, go towards J before you go to N. So we're talking about all of that, LJN. What would be the easiest way to find the measure of that arc? Very good. We want everything in the circle except these parts right here, which are 40 and 25 degrees. So we could add 40 plus 25, and what do we get? 65. And so we take that from the entire circle 360. What's 360 minus 65? 295. Again, for today's lesson, I want to remind you the reason that the arc is the same as the angle is because these are central angles. Next week, they won't always be central angles, so they won't always be the same. But for now, they are. Any questions? Okay, a couple of other things in our notes really quickly before we're done today. So, congruent arcs. Did we already do? No, we didn't. We did congruent. We did adjacent arcs. Congruent arcs are two arcs that have the same measure, but they have to be in the same circles or in congruent circles. Here's what is confusing. Look at the board over here with me. Actually, I'll do it here in case people are watching the video. I'm going to draw a circle here. I'm going to draw a circle here. This is 30 degrees, so this is 30 degrees. This is 30 degrees, so this is 30 degrees. Are those two arcs congruent? Is this arc the same size as this arc? I took my pencil and drew this arc. Is it going to be the same amount of lead as it would be to draw this arc? No. So congruent arcs does not just mean congruent measure, which it has for everything else. Be careful. To be congruent arcs, they have to come from the same size circles. If the circles are the same size and they have the same measure, then they're congruent. So if we had two circles with the same size radius, then the measures of the arcs were the same, they would be congruent arcs. So it says within a circle or congruent circles. So either it's coming from the same circle, in other words, would these two arcs be congruent? These two. Yes, because it's in the same circle and they're both 30 degrees. Or if I drew another circle that was the same size and told you this was 30 degrees, then these arcs would have the same measure. So they would be congruent. Okay, so just be really careful. They have to be congruent circles or the same circle. Okay, I think we're down to two more theorems, and then we'll look at the examples. I'm going to go through the theorems first, and then we'll talk about how much time we have left with the examples. This one looks crazy on the board. It looks like it's three different things, but it's really just showing you that you can go in any direction. So here's what I'm going to do. I want you to look at the board with me up here. I'm going to draw a circle. In my circle, I'm going to draw two angles. What did I just tell you right now with those marks about those two angles? They're congruent. They're the same. So here's what this theorem says. It can go any direction. If you have two congruent angles that are central angles at the center, What's going to be true about the arcs that they form? They're going to be congruent. Everybody agree with that? Okay, the extra thing that they're adding in that's new is that means that the chord that they create, those chords will also be congruent. Do you see the chords in the picture? And it can go in any direction. If the two blue chords are congruent, then the two angles are going to be congruent, and the two arcs are going to be congruent. If the two arcs are congruent, then the two angles will be congruent, and the two chords will be congruent. It doesn't matter which one they give you first, the other two will also be congruent. So if they tell you the angles are congruent, the arcs and chords are congruent. If the chords are congruent, the arcs and angles are congruent. If the arcs are congruent, the chords and angles are congruent. Does that make sense? Okay. That would be our third big idea today that you have to know. So this was number 1, this was number 2, this would be number 3. And then the fourth big idea today, fourth theorem. I'm going to skip this example and go to the last theorem, and then we'll come back to these. Is this one. This says, if you have a circle and you have a radius or the diameter or even just a piece of the radius, if the radius, the diameter, or again, even just a piece of the diameter is perpendicular to a chord. So look at this picture. Do you see that the radius and the chord are forming a right angle? Everybody's with me up here? Super important. Corbin, you with me? Okay. So I have a radius, I have a chord. If the radius is perpendicular to the chord, then it is going to bisect the chord. So it's going to split the chord into two congruent parts. And it's going to bisect the arc. It's going to split the arc into two congruent parts. Is everybody with me there? It goes the other direction as well. If, in a circle, the perpendicular bisector of a chord, in other words, if it's perpendicular to the chord and bisecting the chord, then this must be the radius, which makes this whole thing the diameter. I'm going to draw it on the board. So the fourth thing today is if you have a circle and you have any part of the radius or the diameter and it's intersecting a chord. So when I say any part, they may not draw it all the way to the edge. But if you have any part of the radius perpendicular to the chord, it's going to bisect the chord and it's going to bisect the arc. And if it's bisecting the chord and bisecting the arc, it must be a part of the radius. Any questions? Okay, let's try a problem. We'll do the last one and then we'll go backwards. So look at this picture. This is probably the hardest. Did I do it twice? Is it the same problem twice or is it two different? Oh, it's two different ones. Okay, good. So find NP. Don't give up on me yet. We got 5 minutes. Find NP. They want this distance. What kind of segment is this according to today's vocabulary? A chord. Find NP. So if this distance from R to M, what is this called? The radius. This 8 is referring to this little piece. This 9 is referring to this little piece. So what is the length from R to M? 17, and that is the radius. Okay? What did we just learn? If the radius is perpendicular to the chord, what is it doing to the chord? Bisecting it. So these pieces are congruent. Mark that on your picture. That means we only need to find one of those pieces in order to find the whole length from N to P. So I'm going to call this X. Okay, this next step is what you have to just be able to think of to do. A radius goes from the center to any point on the circle. So instead of going from R to M, where could we draw our radius that might be helpful for us? R to N or R to P, either one. So I'm going to draw it from R to N. What did that just create right here? A right triangle. Now let's relabel that right triangle. This is R, this is N, and there's not really a letter right here. What's the distance here on the bottom of my right triangle? Oops. 8. What's the distance from R to N? 17. We just said that the length of the radius was 8 plus 9, or 17. So now can we find this missing side of our right triangle? Yes, what are we going to use? Pythagorean theorem. So 8 squared plus x squared equals 17 squared. This is also a very common Pythagorean triple. You've probably seen it several times, even just this school year. 8, 17, and then this missing x value. If you know what that is, you can just write it down. If you don't, you'll need to solve it. 64 plus x squared equals, what's 17 squared? 289. Subtract 64, what do we get for x squared? 225. If you take the square root of 225, what is x? 15. 8, 15, 17 is a very common triple. So that means this distance here is 15. So what is this distance here? 15. So what's the length from N to P? 30. So the hardest part there is just making sure that you draw your radius to another location. Do not put a line segment above NP. Okay, I want you to look at one more problem that we didn't do, to go back to here. So we'll just do this one. Okay, and then we'll skip the other one. It's basically the same idea. So find this example, 3B. Should be the very top left corner of that same page. You with me? All right, so look at the picture. If these angles are congruent, what do we now also know is congruent? The arcs, what else? And the chords. So looking at this picture, what could we do then? Set them equal to each other. 14t minus 26 equals 5t plus 1. And then just solve for t. Does that make sense? Okay, go ahead and do that. What would we get for t? Subtract 5t. We get 9t minus 26 equals 1. Add 26. 9t equals 27. So whoever said 3 is correct. T equals 3. If t is 3, is that our answer? No, what did it ask for? NM, so we would go back down here. What's 5 times 3 plus 1? 16. Do not put a line segment over NM when you give your answer. It's a lot of information. So practice by doing your homework, and then it's going to sink in what you're doing if you do the homework. It's not terrible long if you understand the theorems, but you may have to look back at your notes. Use your notes. That's why I give them to you. Okay, hold on one second.